All right, guys, we're looking at section 4.1 today. So as you can see, this is talking about probability and counting rules. So basically, when you think about probability, you are talking in terms of what is the chance of something happening. So as you can see from your notes here, we're talking about from the time we wake up till we go to bed, we are making decisions about any kind of possibility of these events happening. What is the chance of rain shower? So should you carry an umbrella to work today? Is your car battery going to last till spring? Should you accept that new job? So when we're talking in terms of probability, we're saying as a general concept, it can be defined as the chance of an event occurring or the chance of an event happening. So here, as you can see, we're talking about, you should be familiar with the idea of probability from observing or playing games of chance. So games of chance can be card games if you're playing at the slot machines, if you play the lottery. And also you can think of probability being used in the fields of insurance. We use probability in investments, of course, weather forecasting, and different areas where, again, you would be talking about chance. So basically, up until now, we had talked about descriptive statistics. Now we're getting into inferential statistics, which is where we study probability. So we will be talking about, making predictions based on probability. We'll talk a little bit about hypotheses, testing using probability. And then, again, depending on how this semester goes, we will have to see if we can get in depth into these concepts or if we'll just be doing some basic concept and not getting so much in depth. Alrighty, so let's go ahead and look at the different concepts of probability that we would be looking at. So we will talk about probability experiments. We're of course going to talk about sample spaces. In this chapter, we're also going to look at the addition and multiplication rules and the probability of complementary events. We'll also talk about permutations and combinations as we move forward with this chapter. So let's actually start out by talking about sample spaces and probability. So in this case, we're basically looking at examples of what happens when you toss a coin or you roll a dice or if you're playing cards. So based on these kind of examples, we'll try and see how we can come up with sample spaces and probability, and then of course try to use them in other examples. So all of these games that we are playing, such as you're flipping the coin, rolling a die, or drawing a card from a deck, all of these would be called as probability experiments. So as you can see from your definition here, a probability experiment is a chance process that leads to well-defined results called outcomes. So again, a probability experiment is a chance process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. So if you look at these single trials that we're talking about, a trial can mean flipping a coin once, rolling a die once, or something similar. So if you're thinking about tossing a coin, think about it. There are only two things that can happen. You can either get the head or the tail, right? There are only two outcomes because your coin only has two faces. Now, of course, in this case, we're talking about the possibility that your coin ends up landing on its edge. Probably a rarity, doesn't happen that often. So of course, we're going to exclude that. So we're only looking at either you get a head or a tail when you toss a coin. Same thing if you're talking about rolling a die. Again, a common die would have 6 possible outcomes. It would have 6 faces, right? So you would have just the faces with either the 1 dot, 2 dots, all the way up to 6 dots. So in this case, we would actually say then you have 6 possible outcomes, which all of those outcomes together would form your sample space. So we are saying a sample space is the set of all possible outcomes of a probability experiment. So you can kind of see in this little box here, we've got our experiment and what its sample space would look like. So if you're just tossing a coin, like we said, we're only looking at 2 possibilities here. You can have either the head or the tail. So those would be 2 outcomes. Together, they form your sample space for rolling a die. You have 6 possible outcomes. You can get 1 to anywhere of the 6 dots showing up. If you're looking at a true and false question, then of course, again, the idea would be you either answer the question as true or answer the question as false. So 2 outcomes in that. Now, here's the second interesting experiment we have here. If we're talking about tossing 2 coins. So if you're tossing 2 coins at the same time, then your possibilities will be, of course, for each coin, you're still looking at heads and tails. But with 2 coins being tossed together, are both those coins going to land on a head? Are both those coins going to land on a tail? Or will the first one be a head, second one be a tail, first one be a tail, second one be a head? So based on that, you can see you actually end up getting 4 outcomes in your sample space when you're tossing 2 coins. But when we were tossing only 1 coin, we only had 2 outcomes, which was 1 head, 1 tail. So, these will be the kind of things that we will be looking at as we are going through our examples here. So again, in this little paragraph here, you can see we're talking about the importance of realizing that when 2 coins are tossed, you have 4 possible outcomes here. And in this case, they're basically talking about you can use H as an abbreviation for heads, tail as an abbreviation for tails, and then those are the abbreviations we'll be using whenever we're talking about tossing coins in here. So you can kind of read that paragraph on your own. So let's look at our first example here. They basically want us to come up with a sample space for rolling 2 dice. So just like we were tossing 2 coins, if you're rolling 2 dice, then remember each dice will go from an outcome of 1 to 6. So now again, the idea is what are the possible outcomes you can have when you roll 2 dice. So if you look at this little box here, you can see we can have die 1, which is on the, I guess you can think of it as the vertical, the columns, and die 2, which is listed horizontally here. So if I roll these 2 die, I can basically get both of my die falling on 1 and 1, right? So that means both the faces of our die are going to be 1 and 1. Now you can have the possibility where the first die falls on a 2, the second one falls on a 1, or you can have the possibility where the first die falls on a 1 and the second one falls on a 2. So you just, depending on which face you end up going, you will actually see we have a total of 36 outcomes that we are getting when we are rolling 2 dice over here. So if you count all of these, they will add up to 36. And that's because each roll of a dice can give us 6 possible outcomes. So that's 6 times 6 for rolling 2 dice at the same time, which gives you the 36 outcomes. In that same way, we're talking about how can we find the sample space for drawing 1 card from an ordinary deck of cards. So when they're talking about ordinary deck of cards, they specifically mean that you will have 4 suits, which will be the hearts, clubs, diamonds, and spades. We're not including any jokers in there. We're not including any of the other extra cards that you have in there. So basically you have your 4 suits of your cards, and then each of those suits has 13 cards. So that means we will have a total of 52 cards in our deck. So you can see our cards, of course, goes from an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have the jack, the queen, and the king, and that's going to be for your hearts, diamonds, spade, and clubs, right? So that's going to be your sample space for drawing a card from a single card from an ordinary deck of cards. So in this case, you will have a total of 52 outcomes. Again, we've got just a bunch of different examples here, again, talking in terms of what would be the sample space for the gender of the children in a family that has 3 children. So in this case, they're asking us to use B for boy and G for girl. So they basically want to know if a family has 3 kids, what could be the genders for those 3 kids? What are the possibilities? Because again, we don't know specifically what they have, but they just want to know what outcomes are possible. So as you can see here, all three of those kids could be boys. We could have 2 boys and 1 girl. But, you know, in this case, it's actually depending on in which order the kids were born, right? So here you will see there are 2 boys and a girl, which means the third child was a girl. Here, we still have 2 boys and 1 girl, but you will notice that it's boy for the first one, girl for the second one, and boy again for the third one. Or you again have 2 boys and 1 girl, but girl is the oldest one, and then the other 2 after her are the boys. So even though these are all the same number of boys and girls, you will see the order is different because that's based on, you know, the gender of the first, second, and third child in that order. Now, in that same way, you could have all 3 kids being girls. You could have 2 girls for the first and then boy for the last one. You could have girl, boy, girl, and then you could have boy, girl, and girl. So again, for these last 3 options, again, that's 2 girls and 1 boy. But again, you can see that it comes out to be, again, in what order were those kids born. So in this case, the order makes a big difference in your number of outcomes. Okay. So in this case, again, keep in mind, we are listing what the different ideas would be, and they're talking about coming up with these outcomes using a tree diagram. So sometimes, you know, it's easier to visualize what kind of outcomes we will have by drawing this tree diagram. So as you can see from the definition here, we're saying a tree diagram is a device that consists of line segments emanating from a starting point and also from the outcome point. It is used to determine all possible outcomes of a probability experiment. So we're actually going back to the same example here, example 3 of the gender of 3 children. So they're asking us to use a tree diagram to find the sample space for the gender of 3 children in the family. So the idea here is when we first start out, and again, you know, this is just your starting point, so you don't need to put anything here. So that's just going to be blank right here. So now they're telling us that for the first child, we know the option could be they either have a boy or a girl, right? So that's going to be, you start with your 2 branches. First child can be a boy or a girl. Now for the second child, let's say we started out with a boy, which means the second child again could be either a boy or a girl. But if we had girl as our first child, then that means the second one could again be a boy or a girl. So you have to create a branch starting from each child and get 2 more options here. And then now, since we have 4 options for the second child, from each one of these, we again need to draw branches coming out for boy, girl, for all 4 of those options, which will actually end up giving you 8 options. And then we have to try and put this together. So you will see the boy, boy, and boy forms our first option. Then going from boy, boy to girl forms our second option. Then going from boy to girl to boy is your third option. Going from boy to girl is your fourth option. And then using those same ideas, you will be able to come up with girl, boy, boy on the 5th, girl, boy, girl on the 6th, girl, girl, boy, and then of course all 3 girls for the 7th and the 8th options respectively. So you can kind of see how that tree diagram works. Now, if you look at all of these 8 outcomes, they are going to be the exact same ones that we had here. So this one here that was just basically based on observation that we came up with these, or you can use this tree diagram. And I actually like the tree diagram better because, like I said, sometimes having that visual kind of helps you out a little bit better, so you can kind of see how we came up with these sample space for this example here. Alrighty, so the next part is basically talking about what's the difference between an event and outcomes. So when you're talking about an event can actually consist a set of outcomes of a probability experiment. So they're saying an event can be one outcome, an event can be more than one outcome. An event with one outcome is of course called a simple event. A compound event would be if it contains more than one, basically two or more outcomes, or it contains two or more simple events. So simple event is just one outcome. Compound event would be two or more outcomes. Okay, so we're going to break our probability down into three basic interpretations. You've got classical probability, empirical or relative frequency probability, and then subjective probability. Okay, so let's start by talking about classical probability first. So classical probability here is saying that it uses sample spaces to determine the numerical probability that an event will happen. They're saying you don't actually perform the experiment to find this probability. Classical is named because it was the first type of probability that was, formally studied. Now, this is the interesting part about classical probability, and that's this little statement right here in italics. So it's saying classical probability assumes that all outcomes in the sample space are equally likely to occur. So that means that all outcomes in the sample space that you have as part of this classical probability are going to have the same chance to occur or the same chance to happen. So when we're talking about, rolling a die, basically the idea is either you get 1 or a 6 or a 4. When you roll a die, the chance of getting any of those numbers is going to have the same outcome, the same chance of occurring. So they're saying each outcome will have the same probability of occurring. Now, since there are 6 total outcomes, each outcome will have a probability of 1 out of 6. Think about flipping a coin. If you flip a coin, you're going to get either a head or a tail. So that's 2 outcomes, which means the probability of getting a tail is going to be 1 out of 2. The probability of getting a head is going to be 1 out of 2. In that same sense, they're talking about what happens when you select a card from a deck of 52 cards. So, if you're shuffling the deck and you're just picking one card out of that deck, then the idea is the chance of getting a 3 of hearts or an ace of clubs is going to have the same chance, which will be 1 out of 52. So classical probability basically makes the assumption that all your outcomes in the sample space are going to have the same chance, drop my book, have the same chance of occurring, or basically all the outcomes will have the same probability. Okay. Alrighty, here they're talking about equally likely events are the events that have the same probability of occurring. So rolling a die, flipping a coin, or selecting a card out of a deck are all going to be equally likely events. Okay, here they're talking about the formula for classical probability. So you can see basically we're talking about what is the probability of event E happening. So they're saying the probability of any event is going to be how many outcomes do you have in event E, and then how many outcomes do you have in your sample space. So outcomes in your event E will go on the top. Outcomes in your sample space will go on the bottom. So you can see we're defining this as the probability of event E happening, which is P of E, is equal to the total number of outcomes you have in event E, that's N of E on the top. And then the total number of outcomes in your sample space, that's N of S on the bottom. So N of E, number of outcomes in E, N of S is the number of outcomes in sample space. Alrighty, so how about probabilities? Now, we've talked a little bit about probabilities. We didn't quite get into that in depth. In the first 3 chapters, we kind of just hinted on them. But keep in mind that your probabilities can be written as fractions or decimals. And only in certain instances, depending on the example, so they're saying where appropriate, you might also write probabilities as percentages. But for the most part, we actually write probabilities as fractions or decimals. And again, since we are talking about fractions, make sure you're always reducing your fraction and putting it in the lowest form. So fractions in the lowest form or decimals, and then when appropriate, we'll write them as percentages. So just to look at this little line over here, they're saying what is the probability of getting ahead when a coin is tossed. So in this case, you're talking about, you know, out of two outcomes of head or tail, what's the probability that you get a head? That's going to be 1 out of 2. So you can say either it's 1/2. As a decimal, that would be 0.5. And as a percent, you know, half or 0.5 basically translates to 50%. Now look at this little paragraph here inside the parentheses. We are saying, strictly speaking, a percent is not a probability. However, in everyday language, probabilities are often expressed as percents. So basically, you can think of an example of there's a 60% chance of rain tomorrow, you know, something like that. So for this reason, some probabilities may be expressed as percents throughout this book, but, you know, we're going to try and stick to fractions or decimals in this case. So again, your rounding rule for probabilities, keep in mind that you're either writing them as reduced fractions. So either write your probabilities as reduced fractions, or as decimals, you're going to round it to 3 decimal places. And you should actually have this as part of your note cards that I gave you at the beginning of the semester. So just make sure that your note cards have this in them. So here they're saying, what happens if your probability of an event is extremely small? So something like this guy over here, you can see you've got 0.0000587. That's a really small number. So they are saying for numbers like these that are extremely small decimals, it is permissible to round the decimal to the first non-zero digit. So your first non-zero digit in this number would be 5. The 5 is followed by the 8, so that means you round up, and this number will then become 0.00006. So that's how the rounding rule will work. If you don't have extremely small numbers, then you round it to 3 decimal places. But since our third decimal place in this case would be a 0, you're going to the first non-zero digit and rounding it to basically 0.00006, okay? They are saying when obtaining probabilities from one of the tables in Appendix 6, you will use the number of decimal places that's given in the table, okay? And if decimals are converted to percentages, then move your decimal 2 places to the right and add a % sign, so you should be comfortable doing that anyways, right? All right, how about we look at some examples, and then we'll come back and talk about finding the probability, starting with example 5. I actually want to look at some examples before we go on and talk about how to come up with our sample space like we did in these first couple examples. So let's do that next. Okay, guys, so let's look at this example number 40 from your textbook, section 4.1. So this is basically asking us to come up with a sample space using a tree diagram, sorry. So this one is basically saying, let's say you're starting out by tossing a coin. So if the coin falls heads up, you toss the coin again. If the coin falls tails up, then we roll a die, okay? So starting out by tossing a coin. So let's take a look at this example here. So this is number 40. So the first one, they are asking us to toss a coin, right? So if you toss a coin, you can get heads or tails. Now they are saying in the example that a coin is tossed. If it falls heads up, you toss the coin again, which means we will be tossing the coin again, which means you can get a heads or a tails if you toss it again, right? They are telling us, however, if the coin falls tails up, then we are rolling a die. So think about this. If you are rolling a die, that means you can get 6 outcomes where you're going from 1, 2, 3, 4, 5, and 6, right? Because rolling a die will give you 6 outcomes, anywhere from 1 to 6 dots. Okay. So they're basically asking us to draw the tree diagram, which is what I just did, and determine the outcome. So determine the outcomes means what are the different types of outcomes we can get. So from this experiment, if we got a heads, we had to toss the coin again, which means we can get another heads from that. Or if we got a heads and we toss the coin again and we got a tails, so these would be the first 2 outcomes coming from here. But if we got tails first, then that means we would be rolling a die after that, which means our outcomes would then be T1, T2, so that's tails 1, tails 2, 3, T3, T4, T5, and T6. So all of these would be our outcomes. So all, what is that, 8 of these events would, outcomes would be part of our events here. Okay, so that's pretty much what they're asking you to do here. You will see examples similar to this in your homework, so just make sure you're kind of following this example. So now that we've looked at an example for a sample space, let's come back to our probabilities here, and let's look through these examples for how to calculate probabilities. So our example 5 here is talking about finding the probability of getting a black 6 when you are drawing one card from a ordinary deck, right? Randomly selecting a card from an ordinary deck. So if you think about an ordinary deck which has 52 cards, and you can actually go back to this sample space right here. So you can see we can get a black 6 either from the clubs or the spades suite, right? So since we can get 2 6s out of that, so when we're talking about finding the probability of getting a black 6, since there are 2 6 which are from the black suits, you can see that's going to be 2 out of 52. Remember what I told you, reduce your fraction, so that ends up becoming 1 over 26, which of course will be approximately 0.038. So again, we either write our probability as a fraction or as a decimal. If it's not a smaller decimal number, then remember you are rounding it to 3 decimal places here. Okay. Okay, now let's look at example 6 here. This is, again, we're saying a family has 3 children. So what's the probability that exactly 2 of the 3 children will be boys? So this is actually, again, going back to this example we had talked about earlier. So you can look at the sample space from here, or you can look at the sample space from here. So they want to know what is the probability that exactly 2 of the kids will be boys. So we know that's going to happen here, 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 and here, right? Where at least 2 of the kids are boys. So if you come back to this example here, sorry, just a second. They are saying exactly 2 of the 3 children are boys. So that actually means we cannot use this first option where all 3 of them are boys. They want to know exactly when are 2 of the kids going to be boys. So that's actually going to be these 3 outcomes. So we cannot use the first one here. So that means out of the 3 children, exactly 2 boys only happens in 3 different outcomes. So that's going to be these 3 outcomes here out of the total 8 we have, and that gives you a probability of 3/8. Or again, if you want to convert that to a decimal, you can do that. Just make sure you're rounding it to 3 decimal places. So that probability comes out to be 3/8. Okay. So Let's take a look at this paragraph here. Again, I'm not going to read through all of it, so just make sure you're reading these handouts before you come for class, so you're kind of aware of what we're talking about. So they're basically talking about the importance of the meaning of the words and versus or. So when we are saying, if you were asked to find the probability of getting a queen and a heart when you're drawing a single card from a deck, that basically means you are looking for a card which is both queen and heart, right? So which means you're looking for the queen of hearts. So here the word and means at the same time. Now, when you're talking about the word or, that can actually have two different meanings. So here we're talking about, again, what is the probability of selecting a card that is a queen or a heart when you're selecting a card from a deck. So that actually means you can get any of the four, any of the four queens, right, from the four different suits, or you can have any one of the 13 heart cards. So in this case, you would actually say, okay, there are four queens in the whole deck of cards. There are 13 hearts in the whole deck of cards. So that's 4 plus 13. But we know one card falls under both categories. So that would be the Queen of Hearts, which actually will be counted in the 13 heart cards. And also it will be counted in the 4 queen cards. So that's why we actually have to take that duplication off. And so you have to subtract that 1 because that 1 card is common between both sets. So if it's already being counted under the queen, the 4 queens, you don't want it counted for a second time under the 13 hearts. So that's why we're going to subtract that, which gives you a total of 16 possibilities. So of course, then you can do 16 out of 52 to get your probability. Now, so in this case, we are talking about the or, where that same card can actually fall under both categories. Now, you could also be asked to find the probability where they're saying, okay, are you getting a queen or a king? So in this case, you would have 4 queens and 4 kings, right? So you would do 4 plus 4, which is 8 possibilities. And then you would do 8 out of 52 to find your probability. So as you can see, there's a different way that we're using this or word. So you can either have the inclusive or, which is what happened when we did the queen or the heart here in the first example, or you can have the exclusive or, where you have a card that you're choosing whether it's going to be a king or a queen. So in this case, your card does not fall into both categories, which means your both events cannot occur at the same time. That's what we call as exclusive or. So if you're finding a queen or a king card, that's an exclusive or, because my card at the same time cannot be a king and a queen, right? So that's when we're saying the events cannot occur at the same time. However, when we were looking at the example here, where we were talking about selecting a card which is a queen or a heart, since we can have a queen or a heart at the same time, that's where saying both events occur at the same time, and that's your inclusive or in that case. Okay, so it actually makes a difference on what kind of probability you are looking at, and then based on inclusive or exclusive or, you're going to have to decide how to calculate your probability. So that's what this little example here is talking about. So we're drawing a card from an ordinary deck. They want to know what's the probability that the card we select is a heart. So remember, there are 13 heart cards in a deck. So that will be 13 out of 52. Reduce that fraction, you get 1/4 or 0.25 as your probability. They want to know what is the probability of getting a black card. So remember, that can be either diamonds or spades. So that's a total of 26 cards. And since it's total of 26, that's going to be 26 out of 52 or 1/2, 0.5 as your probability. Now, what about getting just the 8 of diamonds? So 8 of diamonds is only going to be 1 card out of the entire deck of 52 cards. So that's why it's going to be 1 out of 52 or approximately 0.019 as your probability. What's the chance that we select the card is a queen? So again, remember, there are 4 queens in a deck. So that would be 4 out of 52 or 1 out of 13 for a probability of 0.077. Now, when we're talking about a face card is going to be your Jack, Queen, and King cards, right? So there's going to be 3 face cards in each suit. And since we know there are 4 suits, that's going to be a total of 12 face cards in the deck. So that's going to be 12 out of 52 or 3 out of 13 for approximately 0.231 as your probability. Okay, so you can kind of look through this example and see if you have any questions. So here, we're just talking about some basic rules for probability. So as you can see from the first one, we're saying the probability of an event is a number, again, either as a fraction or a decimal, which will be between and including 0 and 1. So when we're talking about probability of an event, we denote that as P of E. And we're basically saying the probability of an event can fall anywhere from 0 to 1. You can actually include the endpoints. So you can have a probability of 0. You can have a probability of 1. So probability of 0 basically means that that event has no chance of occurring, which means that event will not happen. So think about it this way. If we are talking about rolling a die, which has 6 faces, it goes from 1 through 6, and somebody asks us, what's the probability that I roll a die and I get 8 as an answer, that would be a probability of 0, right? Because this dice that we're rolling does not have a face of 8 on it. It only goes from 1 through 6. However, for that same die, if somebody asked us, what's the probability that you would get a sum of, I don't know, 7. Well, that would again be a probability of 0 because again, you're not going to get a 7 out of that phase because again, your phase only goes from 1 through 6. Okay, so you kind of have to think about it in that terms. Anything in between is okay. So if they ask you what is the probability of rolling a die and getting a 6, well, that is 1 out of 6, which will be a number that falls between 0 and 1. Now, rule number 2 is talking about the sum of the probabilities of all outcomes in the sample space is going to be 1. So that's basically, think about it. If I look at tossing a coin, I can get a head or a tail. So the probability of getting a head is 1.5 or 0.5. The probability of getting a tail is 1/2 or 0.5. So if I add 1/2 and 1/2, I am going to get a total of 1, right? So again, think about tossing a coin. So the probability of getting a head is 1/2. The probability of getting a tail is 1/2. So if I add 1/2 with 1/2, I get 1, right? You can do the same thing with the decimal. If you add 0.5 with 0.5, you still get 1. So that's what they're talking about here in rule 2, is the sum of all probabilities in the sample space is going to be 1. Rule 3 here is talking about if an event E cannot occur, they're saying basically there are no members in that sample space, that probability is going to be 0. So kind of how I was talking about rolling a die and asking for a 7 or an 8, that's not possible. If an event is certain, which means you know it's going to happen, then its probability is going to be 1. So you are basically saying there's 100% chance that this event is going to occur and its probability is going to be 1. Okay? So these are the rules that you're going to have to remember. Your probability can be anywhere from 0 to 1, including 0 and 1. The total of your sample space, the probabilities has to add up to 1. If the event has no chance of occurring, its probability will be 0. If the event is certain, you know it's going to happen, then its probability is going to be 1. Okay? And then you can kind of see this little range of probability horizontal axis here that they have where it's going from 0 to 1. So of course, remember what we said, if the event cannot happen, it will have a probability of 0. So that means that event is impossible to happen. If it's certain that that event will happen, it will be at 1. So we know it's a 100% chance of happening. Now, anywhere in the middle, so right halfway through, you have your 50% chance. So we would say, okay, it's 50-50. So either it's going to rain today or it's not going to rain today. We'll see. If it's anywhere between 0 and that 50% chance, so anywhere between 0 and 0.5, we would say the event happening is unlikely. If it's between 0.5 and 1, then we say the event is likely to happen, which means there's a good chance it will happen. Okay, so again, between 0 and 0.5, the event is unlikely to happen. Between 0.5 and 1, the event is likely to happen. Okay. And then here, they're actually talking about rule number 2, which is where they said that if you add the sample space, the probabilities of all outcomes in your sample space, it should add up to 1. So that's what this one is talking about. So this is actually rolling a die. So if you get the face of 1, we know it has a probability of 1/6. If you get a face of 2, that also has a probability of 1/6, and same thing for all the other faces. So if I add all of these 1/6, 1/6, 1/6, it adds up to 6/6, which actually comes out to be 1. Okay. All right, let's look through these examples here, and then we'll pick an example from our textbook. So again, they're talking about when a single die is rolled, find the probability of getting a 9. So we know a single die only goes from 1, 2, 3, 4, 5, and 6 on the faces, which means 9 is not a possibility. So that means the probability of 9 is going to be 0. So this is an event that is impossible to occur, and it's going to end up getting 0. Okay, now what about, again, we roll a single die, and this time they want to know what is the probability of getting a number less than 7? Well, we know all of these numbers are less than 7, right? So if we get any one of these as our answer, they are all going to be less than 7, which means the probability of getting a number less than 7 is going to be 6/6, which is a total of 1, right? 6 divided by 6. So in this case, we would say when you roll a die, the certainty of getting a number less than 7 is going to be 1, because our probability is 1. We know this event is certain. Okay? So this was kind of an example to show you when an event is not going to occur, which was right here when they asked us to find the probability of 9 in example 8. So this is a probability of 0. In example 9, where they're saying what's the probability of getting a number less than 7? Well, that's a probability of 100%, or 1, because we know all these numbers, 1, 2, 3, 4, 5, and 6, are all going to be less than 7. So there's a good chance we land on one of these numbers, so our probability is going to be 1. Okay? All right, so let's stop right here and look at an example. Okay, so let's look at example 13 over here. We're talking about rolling a die. So if a die is rolled one time, find these probabilities. So let's take a look at the first one here. So what's the probability that we get a 7? So again, keep in mind, when you are rolling a die, your outcomes are going to be 1, 2, 3, 4, 5, and 6, right? So you can see none of these are going to have 7 as an answer, so we're not going to get a 7, which means the probability of getting a 7 is actually going to be 0, because we're not going to get a 7. Now, what is the probability that we get an odd number? So you can see our odd numbers are going to be 1, 3, and 5, right? So that's 1, 2, 3 out of a total of 6 outcomes, which is 1/2 or 0.5, okay? What is the probability of getting a number less than 7? Well, all of these numbers are less than 7, which means the probability of getting less than 7 is going to be 1. And this is actually similar to the example we just looked at in our handout. All right, now this is interesting. The part D is saying what is the probability of getting a prime number? And of course, your prime numbers are 2, 3, or 5. So 2, 3, or 5, that's again 3 outcomes out of a total of 6. So that's going to be 1/2 or 0.5. Okay, so that's kind of how you would have to look at. So remember, the probability is always the outcomes that are in your event divided by the outcomes that are in your sample space. All right, let's look at one more example here. So hold on a second. Okay. How about we look at number 15 next? So here they're talking about if 2 dice are rolled at one time, find the probability of getting these results. So what is the probability that we get a sum of 5? So for rolling the 2 dice, we're actually going to have to go back to our notes here. And let me see if I can actually cancel this for now. And let's get back here. Okay, here's our sample space. So what is the probability that we are going to get a sum of 5, which means when I add these outcomes, they should add up to 5. So if you think about this, the sum of 5, these guys are adding up to 2, this is 3, this is 4, this is 5. And then 2 plus 3 will be 5, 3 plus 2 will be 5, 4 plus 1 will be 5. Anything below that, that's 3 and 1, which is 4, 2 and 2 is 4, 1 and 3 is 4. Of course, these guys are 3, this is 2. Now, if you go above that, 1 and 5 is going to be 6, 2 and 4 is going to be 6, 3 and 3 is going to be 6, 4 and 2 is going to be 6, 5 and 1 is going to be 6. So it's only going to be these 4 outcomes. So that's 1, 4, 2, 3, 3, 2, and 4, 1, right? So that's 1, 2, 3, 4. Okay, let's go back here. So that's going to be 4 out of a total of 36 outcomes. So you can reduce this. 4 goes into itself 1 time. 4 goes into 36 9 times. So this will become 1/9. And then if you want to do this as a decimal approximation, let's see, that guy will come out to be approximately 0.111. And that's actually repeating ones. So to 3 decimal places is just 0.111. Okay. Now this one here is saying what's the probability that it's going to be a sum of 9 or 10. So 9 or 10, we know this is not going to be inclusive because you either have a sum of 9 or you have a sum of 10. So that's going to be an exclusive or. So in this case, let me move this guy down a little bit here. We're looking for a sum of 9 or 10. So that's going to be 6 plus 3 is 9. 5 plus 4 is 9. 4 plus 5 is 9. 3 plus 6 is 9. They also said or 10. So 6 plus 4 is 10. 5 and 5 is 10. 4 and 6 is 10, right? Anything less than that, 6 and 2 would only be 8. So we don't use that. 5 and 3 is 8. Same thing here. 4 and 4 is 8. 3 and 5 is 8. 2 and 6 is 8. So you keep these guys out. 6 and 5 is 11. Keep that out. 5 and 6 is 11. And of course, 6 and 6 will be 12. So that's actually a total of 1, 2, 3, 4, 5, 6, 7 outcomes that will add up to either a 9 or a 10. So again, 1, 2, 3, 4, 5, 6, 7. So that's going to be 7 out of 36. And as a decimal, because of course 7 does not go into 36 evenly, this comes out to be 0.1944 repeating. So 0.194 as decimal. I would actually probably leave this as fractions, but if you really want to do them as decimals, you can. Now they want to know what's the probability of getting doubles. So again, let's go back to our sample space here and the probability of getting doubles. So for doubles, of course, we're talking about 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Let me go ahead and erase some of these older marks so we don't get too confused here. Okay, so doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that's 1, 2, 3, 4, 5, 6. That's going to be 6 out of 36. And of course, 6 goes in itself once. 6 goes into 36 6 times. So you can again get a decimal approximation for this guy, which will be 0.166 repeating. So approximately 0.167. Like I said, I'd probably leave my answers as fractions, but just so you know what the decimal answers look like, I'm putting those here as well. So hopefully this gives you an idea of how we are kind of calculating these probabilities. Again, you're going to see a bunch of different examples in your homework, so look through those. If you have any questions, let me know. Okay. All right, let's go back to our notes again here. So let's look at complementary events. So now when we're talking about complementary events, basically we're talking about, if you look at this example here, we're saying when a die is rolled, the sample spaces consist of 1, 2, 3, 4, 5, and 6, right? So if we're talking about event E being where you get odd numbers, so that means your event E would include the outcomes of 1, 3, and 5, right? So an event where you do not get odd numbers is what we would call as the complement of event E. So an event that does not get odd numbers in it would actually consist of the outcomes of the even numbers, right? 2, 4, and 6. So the way we would actually write this is that event E would have the outcomes, and I'm trying to think how I want to write this. I think I'm going to write it like this. So event E is the odd outcomes, right? So when we're talking about the complement of an event, we actually write it as E bar with a bar on top of the E. So this would include all the remaining events from your sample space that are not odd numbers. So that would be the 2, 4, and 6. So this is actually how you would end up writing the complement of an event. So you can see from that definition, we've got the complement of an event E is the set of outcomes in your sample space that are not included as outcomes of event E. And again, it's denoted with E bar as the complement of an event. So looking through this example here, they're asking us to find the complements for these events. So selecting a month that has 30 days. So if a month has 30 days, then its complement would be the months that don't have 30 days, right? So those would be the months that have 28 days or 31 days. So that would be your January, February, March, May, July, August, October, or December. So these would all be the complementary events. If part B is talking about selecting a day of the week that begins with S, so if the day of the week is beginning with S, then the complement of this event would be the remaining days of the week that do not begin with an S, right? So for S, that would only be Saturday and Sunday, which means the complement of the event would be outcomes including Monday, Tuesday, Wednesday, Thursday, or Friday, right? Rolling 2 dice and getting a number whose sum is 7. So the idea is if you are rolling 2 dice and the sum is 7, which means the complement would go from all the other sums. So you would include sum of 2, 3, 4, 5, 6. You would skip 7 because 7 is the main event. 8, 9, 10, 11, or 12. So all of those sums would then form the complement. Selecting a letter of the alphabet, excluding Y, that is a vowel. So your vowels would be A, E, I, O, U. So basically the complement of the event would be including all the other letters that are not vowels, which is what we call as consonants, right? So then this event, the complement, would be including all the alphabets that are consonants. So the complement of the event, you just kind of have to think about it as whatever you're defining event E to be, whatever does not fall under event E will all, the remaining stuff will go under the complement of the event, which would be E bar. So just look at your sample space. All of the values that you are putting as part of event E, just don't include them in the complement E bar, okay? Okay, let's look at how to find probabilities of complementary events. So we're saying the outcome of an event and the outcome of the complement have to make up your entire sample space, because whatever you are not including in the event E itself, you're including that in the complement, right? So together, they have to make up your sample space. So you should have basically all of these events in your sample space. So that's kind of what this little line here is talking about. So just as an example, we're talking about if 2 coins are tossed, then the sample space is, of course, heads, 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 tails, tails, heads, and tail, tails, right? So if they're saying the complement of getting all heads is not getting all tails, and this is something you have to think about. We are saying that the event is getting all heads. Getting all heads is going to be the 2 heads here. So the complement is actually going to be everything where you're not getting all the heads. So that means you will get at least 1 head and 1 tail and 1 head, or 2 tails. So that means the complement of an event of getting all heads is actually going to be getting at least 1 tail. As you can see, in all of these 3 outcomes, we have at least 1 tail as part of our sample space, okay? So you kind of have to think about whatever is not in the event of getting all heads is what you're putting in the complement, so all the remaining outcomes, okay? So they're saying since the event and its complement makes up the entire space, sample space, it follows that the sum of both the event and the complementary event has to equal 1. So this is going to be something important to keep in mind. So the sum of the probability of the event and the probability of the complement has to equal 1. So if you use that idea, you can actually come up with this rule here for calculating your complementary events. So to find the probability of your complementary event, you can do 1 minus the probability of the event itself. Or if you know the probability of the complementary event, then you can do 1 minus the probability of the complementary event to get the probability of the event. Or basically remember adding up the probability of the event with the probability of the complementary event is going to add up to 1. And then you can see here the rule they're talking about. The rule is if the probability of an event or the probability of its complement is known, then you can find the other by subtracting the probability from 1. So right here. Okay. Here, they're talking about how you can also use Venn diagrams to help you out. So I'm not going to read the paragraph here. Go ahead and do that yourself. So basically here, the idea is since we know the entire sample space is going to have a probability of 1, if this is the probability of event E, then that means this blue on the outside will be the probability of the complementary event. And together, both of these will add up to 1. Same way here, if you know the probability of the complementary event and, sorry, I think this is, if you know the probability of the complementary event, you can do 1 minus the probability of the complementary to get the probability of the event itself, or vice versa. So you can kind of see how these Venn diagrams are designed. So basically the idea is the whole rectangle here adds up to 1. Whatever is the probability of the event, subtract that from the probability of the sample space, which is 1, and you get the probability of the complementary event. Or if you know the probability of the complementary event, subtract 1 minus the probability of the complementary event to get the probability of the event itself. So you can kind of see this example here. They're saying in a study, it was found that 24% of people who were victims of a violent crime were aged 20 to 24. Okay, so basically we're saying 24% of the people who were victims of violent crimes fell between the ages of 20 and 24. So if a person is selected at random, what is the probability that person is younger than 20 or older than 24? Okay, so this is again kind of using the idea of complementary events. So basically, if they're talking about a person being younger than 20 or older than 24, they're basically saying the person does not fall in the age group of 20 to 24, right? So what is the probability that the person is not aged between 20 and 24? You're going to do 1 minus the probability of the people who are aged between 20 and 24. So that's 1 minus 24%, which as a decimal is 0.24. 1 minus 0.24 is 0.76. Or basically, again, as a percent, you can say it's a 76% probability that if you select a person at random, they are going to be aged less than 20 or older than 24. Okay, so let's look at an example for our complementary events. So this is example 31 from your textbook. So they are talking about the number shows the number of crimes committed in a large city. If a crime is selected at random, find the probability that it is a motor vehicle theft. So find the probability it is a motor vehicle theft, and what is the probability it is not an assault. Okay, so let's do the first one, finding the probability of motor vehicle theft. Okay, so of course from your table here, you can see motor vehicle theft is at 275. So that's 275, but then what's our total? So you actually need to go ahead and calculate the total for all the crimes here. So that's going to be 1375 added with 500 plus 275 plus 200 plus 125 and then plus 25. So that actually comes out to be a total of 2,500. So if you take 275 out of 2,500. That comes out to be a probability of 11 out of 100, or as a decimal, 0.11. Okay, so that was the first part. The second part, they're asking us what is the probability that it is not an assault. So this is a complementary event here, which means you have to do 1 minus the probability of an assault. So again, you have to figure out what is the probability of assault. And so again, going back to our table, you can see the numbers of assaults happening in the big city is 200. So you're actually going to do 200 out of 2,500. And then whatever this fraction comes out to be, you're subtracting that from 1. So let's see, what does that come out to be? So that's going to be 1 minus the fraction 200 divided by 2,500. And this one will come out to be, again, this is going to be a reduced fraction. So that's going to be, trying to think how I want to write this. You can write this as 2,300 out of 2,500. If you just do a simple subtraction between those two as a reduced fraction, this would of course be 23 out of 25, and then as a decimal, it's going to be, hold on a second, 0.92. So you have a pretty good chance that it is not going to be an assault, because that's going to be 0.92. That's a pretty high percentage or probability that it's not an assault. And then your motor vehicle theft, you can see it's still a pretty small probability because it's 11 out of 100, or basically 0.11 or 11%. So I kind of hope this gives you an idea of how we go about calculating probability of a complementary event. Okay, so we've talked about classical probability. We looked at the complementary events. Now let's talk about empirical probability. So basically the difference between classical and empirical, like we talked about in classical, we're basically assuming that each event has an equally likely chance of occurring. So how we talked about with our tossing of a coin or rolling a die, you're going to be looking at the same probability for all outcomes. But when we're talking about empirical probability, we're basically saying this relies on actual experience to see what the likelihood of the outcomes will be. So in empirical probability, they're saying, let's say, okay, one might actually roll a given die 6,000 times. And then based on those observations, we may see what the frequency of an outcome is. So if you're rolling the die 6,000 times, and out of those 6,000 times, 500 of the times gave you the number 1, then we would say it's 500 out of 6,000 as the probability, right? Whereas in classical probability, we would say by our reasoning that 1,000 of those rolls, I guess, should come out to be 1 out of the 6,000, because we know from classical probability that the chance of getting a 1 when you roll a die is 1 out of 6. So in a classical probability, if you are rolling a die, your probability of getting a 1 is 1/6. But like I said, with empirical probability, what if we did 500 out of 6,000? So if you go ahead and reduce that fraction, you're obviously not going to get 1/6, right? Because this guy will actually come out to be probability of 1/12, 500 out of 6,000 rolls. So this basically tells you that in empirical probability, you would actually depend on the actual observation that you make, as opposed to using a logical reasoning like we do in classical probability to come up with our answer. Okay, so you can see your probability will change. So looking at this example here, they're saying a researcher for the American Automobile Association, or AAA, asked 50 people who travel over the Thanksgiving break, how will they get to their destination? So if you're talking about 50 people, 41 out of the 50 said they're going to drive, 6 are going to fly, and 3 of them said they were either taking a train or a bus, right? So this would be based on actual observation by actually talking to these people and looking at, you know, what they were doing. So in this case, your probability would then be for driving would be 41 out of 50, for flying 6 out of 50, and then of course train or bus would be 3 out of 50. So you can see the formula here for your empirical probability. They're saying given the frequency distribution, the probability of an event would be the frequency of the class. So that's going to be the 41 for the driving out of the total frequencies in your distribution, which would be 50. So then this guy would be 41 out of 50 for the probability of driving over Thanksgiving break, right? So let's take a look at this example here. In the travel survey just described, which is the one we just talked about with Thanksgiving break, what's the probability that a person will travel by train or bus over the Thanksgiving break? So we know 3 people out of 50 said they were going to travel by bus or train. So that's 3 out of 50. And as a decimal, that's about 0.06. Okay? How about this example here? In a sample of 50 people, we're saying 21 have type O blood, 22 had type A, 5 had type B, and 2 people had type AB blood. So again, setting up a frequency distribution, you can kind of see what that frequency distribution looks like right here. Now the question is, the person has type O blood. What's the probability of this? So you can see type O in our table is 21 out of 50. So that's where this 21 out of 50 probability is coming from. For question B, they're asking the person has type A or type B blood. So again, remember, this is going to be the exclusive or we had talked about, because you can either have type A or type B, okay? So that means they're talking about these first 2 categories in our table. So that's going to be 22 out of 50 plus 5 out of 50, which of course adds up to 27 out of 50. Okay, now let's look at this part C here. They're saying a person has neither type A nor type O. So if they're neither type A nor type O, now you can use the idea of a complementary event, or basically if they are not A and O, then they're basically going to be B and AB. So that's going to be 5 people from there, 2 people from there. So you can add the 5 and the 2, which will give you 7 out of 50. So you can do it that way also. Now this last part is definitely going to be a complementary event. So they're saying a person does not have type AB blood. So we're basically saying they do not have type AB, which means they don't have type AB, so they can be any of the other 3 types, A, B, or O. Now you can obviously add the 22 with the 5 and the 21 and get it that way, but since you only have to exclude this one event, type AB, you can actually do 1 minus the probability of AB, which is 1 minus 2 out of 50. So we know there's a total of 50 people. So 2 subtracted from 50 gives you 48, and you get 48 out of 50 or 24 out of 25. So you can do it that way. Or like I said, you could have also added 22 with the 5 and the 21, which would have still added up to 48 out of 50 or 24 out of 25. So it's kind of up to you what you feel comfortable with that. All right, let's look at another example here. So we're talking about sleep hours. A recent survey found the following distribution for the number of hours a person sleeps per night. So there are 12 people who sleep less than 6 hours, 26 people who sleep 6 hours, 30 people who are sleeping 7, 28 people who sleep 8 hours, and only 4 who sleep more than 8 hours. So you can see that adds up to a total of 100 people that were surveyed. So let's take a look at our questions here. So they want to know what's the probability if you select a person at random that this person sleeps 8 hours per night. So this person who sleeps 8 hours per night is of course going to be right here, the 8 hours, which is 28 out of 100. So you would do 28 out of 100, and you would have 7 out of 25 for the number of people who sleep 8 hours per night and what that probability looks like. A person sleeps fewer than 7 hours per night. So when we're talking about person who sleeps fewer than 7 hours per night, that would be a person who sleeps for 6 hours or anybody who sleeps less than 6 hours. So this would be the 26 and 12 together. So 26 plus 12, which gives you 38 out of 10 or 19 out of 50 as your probability. Okay, part C is saying sleeps at most, which means we're saying they are sleeping a maximum of 8 hours per night. So as you can see here in the solution for part C, we are saying at most means they are sleeping 8 hours or less than 8 hours. So that's actually going to include these first 4 categories, the 12, 26, 30, and 28. So you can do it that way. Or you could have actually done that as a complementary event also. And then for part C, you could have done 1 minus, because they are talking about at most, which means more than 8 hours. This would not be included in it. So you could have done 1 minus 4 over 100, which would again give you 96 out of 100, which obviously reduces down to 24 over 25. So you could have done it as a complementary event also, or you could have done it how they showed you here by adding those 4 numbers. Part D here is saying the person sleeps at least, which means at a minimum of 7 hours or more than 7 hours. So for minimum of 7 hours, let me get rid of this here, you would have 7 and more than 7. So that would again be 30, 28, and 4 added together, which is what gives you the final result here, which is 62 out of 100 or 31 out of 50. So you can kind of see how we calculated these probabilities here. Okay. And just the last part that I want to talk about here with empirical probabilities is, as you can see, we're saying empirical probabilities can be found by using a relative frequency distribution. Remember, again, for relative frequency, you take your frequency and divide it by your total. So that would be 41 divided by 50, which gives you the 0.82. If you did 6 divided by 50, that would give you the 0.12. And then, of course, 3 divided by 50 would give you the 0.06. Now, since probabilities have to all add up to 1, obviously you can see all of these here end up adding to a total of 1. Okay, so just kind of keep those probability rules in mind that we had looked at. And then they are saying these frequencies are the same as the relative frequencies we talked about in chapter 2. Remember when we were looking at our histograms, frequency polygons, and ogives, we had talked about relative frequencies, so that's the same discussion that we. All right, so let's take a look at this example, which is example 32. from your textbook. So this is talking about the living arrangements of children under 18 years old living in the United States in a recent year. Okay, and they're telling us these numbers are in thousands. So children living with both parents is at 51,823. Only living with the mother is at 17,283. Only with the father is 2,572. And living with neither parent is at 3,041. Okay, so now they're saying choose one child at random. What is the probability that the child lives with both parents? Okay, so for the first part, child living with both parents, that's of course going to be this one right here. So that's 51,823, and you can see I've already calculated the total for all four of these numbers. So that adds up to 74,719. So that's 74,719. So let's see if we can get an answer here. So let's see, 51,823 divided by 74,719. So I'm not getting a simplified fraction. I guess my calculator doesn't want to do that. But as a decimal approximation, I am getting a probability of 0.694. So you can see that's a pretty good probability there, almost 70%. We're at 0.694, so that's not too bad. Alrighty. So that was the first question. Now, the second one is asking us with the mother present. So what's the probability of children living in a household where the mother? Okay, so when they're talking about mother present, they are saying that it could be both parents, right? Because this is also where the mother is present. And of course, this could be the mother only category. So it's actually going to take the first and the second number into account, because again, remember, with both parents, you have the mother present. If they're living with the mother, then obviously they have the mother present. But if the children are living with the father only, that means the mom is not there. And of course, if they're living with neither of their parents, then again, the mother is not present. So the probability of living with their mother being present is going to be the 51,823 added with the 17,283. So you have to add both probabilities. And again, make sure they are over the total number of children. So this would actually come out to be 51,823 added with 17,283, which is a total of 69,106 over our total of 74,719. And as a probability, this comes out to be approximately, I'm going to write it down here, you've got 0.9248 or approximately 0.925. So those would be your two answers for this example. So with the mother present and living with both parents. Okay, again, look through those examples. Okay, so let's talk about the law of large numbers. Now remember how I was talking about the empirical probability, where by classical probability we know that if we roll a die, the chance of getting a 1 is 1 out of 6, right? But with empirical probability, let's say we roll the die 6,000 times and we only got 500 ones out of that, that would be a probability of 1 out of 12. So what the law of large number really says is that if you do large enough number of trials, that your empirical probability will actually start getting closer to your classical probability. So the idea is, and you can see that right here, they're saying what happens when a coin is tossed 50 times? Will you get 25 heads? Well, that's not going to be true, and you can try this if you like. Should you expect 25 heads? If your coin is fair, then yes, there's a good chance you may get 25 heads, but obviously it's not going to happen that many times. But what the law of large number says, that if you keep tossing that coin and you keep doing this experiment for maybe 1,000 times, 2,000 times, eventually you should see that half of those flips should give you a head and half of those flips should give you a tail. So if you look down here, they're saying in this paragraph, however, as the number of trial increases, the empirical probability of getting a head will approach the theoretical probability of 1/2 if your coin is fair. So this is actually what we call as the phenomena of law of large numbers. The more times you do your experiment, eventually you will actually start approaching that classical probability that we saw with the first part, and the empirical probability will match that classical probability. And if the idea is the coin you are flipping or the die you are rolling, if it does not show this phenomenon of law of large numbers, then that actually means that the die is not fair or the coin is not fair. And as the example is talking about here, your pit bosses in casinos are always looking out for these kind of things. So if they're noticing that the die that they are using in their games, if it's leading towards one of those frequencies a whole lot, and it's not showing an equal chance of falling onto any of the numbers, then a lot of times they will actually switch it out. They will take the dice out of play and replace it with a newer one, just to make sure that they are always going to get that classical probability. And it's not going to be a die that has been modified or something has changed where it's not working out like it's supposed to. Okay, so just to show you how the law of large numbers work. Now, of course, I'm not going to be doing this for too many flips because I don't want to take up too much time. But let's say I'm just flipping one coin, and you can see I got, I guess, a heads here that looks like a euro, one euro Irish coin. If I flip again, I'm on the tail side. That's a head, that's a tail, a head, a tail. It looks like right now my probabilities are actually pretty even. And then I got a bunch of tails there. I'm gonna flip this again. I'm getting a head. Flip it again, it's a head. Flip it again, it's a head. Another flip, it's a head. Now I've got a tail. I've got a head again. I've got a head again. That's a tail. And a head. Head again. That's a tail. Head again. So you can kind of see that every time we flip the coin, you're not always going to get that even result where it's going to give you all heads, like 5 heads in a row and 5 tails in a row. It's going to keep changing. And if we keep a record of how many of these heads and tails we've got, you will see it's not always going to be half and half. But the more of these flips we keep doing, those probabilities are going to get closer and closer to that 1/2 value. So if you guys want to try it, just take out a quarter coin or something and try, I don't know, do it 20 times, maybe do it 30 times, 50 times, and see what kind of probability you are getting. Don't take up too much time because, again, I don't want you to. Okay, so the last thing that we want to talk about in this section is about subjective probability. So we've looked at classical, we have looked at empirical. So this last part, the subjective probabilities, of course, as you can see, And I just lost my page here somewhere. So the subjective probability, as you can see here, is talking about using an educated guess or an estimate by employing opinions and sometimes inexact information. So subjective probability is something that, of course, it will kind of depend on what example you are working with, and does it make sense to have that subjective probability used. So here we're talking about a person or a group makes an educated guess that the chance that an event will occur. So again, it will depend on their experience, the person's experience, how they are evaluating the situation. So they're saying, for example, a sports writer may say that there is a 70% probability that the Pirates will win the pennant next year. So again, obviously, if the sports writer is making this probability, he's probably looking at how the team has played during this season, what their past record has been, and of course the experience he's had as a sports writer to make that educated guess. Now, that's not necessarily going to be true that there's a 70% chance that the Pirates will win, but again, it just kind of depends on the experience. They're saying a physician might say on the basis of her diagnosis that there's a 30% chance the person will need an operation. So same thing, evaluating the situation and then looking at the physician's experience themselves. A seismologist might say there is an 80% probability that an earthquake will occur in this area. And, with subjective, it's going to change because that's kind of how subjective probability works. So one seismologist may say there's an 80% chance for a probability of an earthquake to occur. Another one might say, you know what, I don't think so. I think there's only a 60% chance. So it's going to be very different based on who is making the educated guess, who's coming up with the estimate, and how they're looking at it. So again, remember, we've talked about 3 different types of probability: classical, empirical, and subjective. Remember, in classical, we say that all the events or all the outcomes have an equally likely chance of occurring. In empirical, we are saying that is based on observation, and subjective is basically an educated guess. So this will be something that you will need to distinguish between what kind of probability is being used and which one we are looking at. And then, of course, you can use this idea of probability to solve problems like they're saying here in business, engineering, of course, sports, weather forecasting. I mean, there's a lot of different places where probability is being used. And as we move forward in this chapter, you'll definitely see more of that. Okay, and then this last part here is talking about the probability and risk-taking. Again, I would actually prefer you guys to read this paragraph or this part of the handout on your own rather than me going over it. I'll just highlight some of the things that we want to talk about here. So, like we're talking about, an area in which people fail to understand probability is risk-taking. People fear situations and events that have relatively small probability of happening than those events that have a greater likelihood of happening. So we're talking about, many people think that the crime rate is increasing every year. However, as you can see, we're talking about this book here, How Risk Affects Your Everyday Life by James Walsh. He's saying that despite widespread concern about the number of crimes committed in the United States, the FBI and Justice Department statistics show that the crime rate has actually remained fairly at the same level for the last 20 years. It even dropped slightly in the early 1990s. So it may seem like the crime rate is increasing, but it's actually not. Then in the same book, he's talking about today's most media coverage of risk of health and well-being focuses on shock and outrage. So shock and outrage make good stories. They can scare us about the wrong danger. So he's saying if a person is 20% overweight, the life expectancy is 900 days, about 3 years. But the loss of life expectancy from exposure to radiation is about 0.8 0.02 per day. But, you know, obviously the idea here is the threat of being 20% overweight has a bigger effect on the loss of life expectancy than the exposure to radiation. But of course, as people, we are more afraid of radioactive emission than we are of watching our weight, right? So that's kind of what they're talking about in terms of how we look at probability and the risk factor that's involved with it. They're talking about people gambling their lives on a daily basis by using tobacco, or, you know, for that matter, any vaping product, by drinking, driving, riding motorcycles. So if you again compare what the risk factors are here, then you know, you can kind of look at, okay, well, these are activities we still do, but we don't really think about how much effect this can have on our life expectancy. So again, that might be something to kind of consider. So again, you can kind of look through that paragraph. They're talking about the overestimation of causes such as accidents, fire, and flood, and they're underestimating the probability of death from diseases, from strokes and stuff like that. So you can kind of look at that. This example here, they're talking about most people think that their chances of dying of a heart attack are 1 in 20, when in fact, that's almost 1 in 3. The chances of dying from pesticide poisoning is 1 in 200,000. But of course, we would be thinking more about pesticides than we would be worrying about heart attacks. So that could be something to think about. This next paragraph here is talking about life-threatening catastrophes such as hurricanes, floods, automobile accidents. We know how dangerous texting while driving is. So those could be some numbers that, you know, we don't kind of think about them as much as what we should be. And then again, what kind of threat level is presented when you are looking at the actual numbers. So that could be something you would have to think about. So again, like I said, read through this last part here and kind of see what they are talking about. So mainly in this section, we have talked about how to calculate or come up with our sample space, and then how to talk about probabilities based on the event and the outcomes you're looking at, and then looking at your entire sample space. And we did this in 3 different forms of probability by using classical, empirical, and of course, subjective as our last one. All right, guys, so that's the end of section 4.1.